Muito boa tarde. Good afternoon to those of you that speak English. Vamos dar início a mais uma sessão plenária, a segunda sessão plenária de hoje, que tem como tema de fundo as comemorações dos 150 anos da Tabela Periódica. Como sabem, a Unesco definiu este ano como símbolo a Tabela Periódica. E se muitas das atividades sociais, económicas e científicas hoje são uma realidade, devem-se muito àquilo que foram os princípios científicos que tiveram na base da Tabela Periódica. Uma das questões críticas hoje que se põe no desenvolvimento económico e na sua melhor compatibilidade com os compromissos da preservação ambiental tem a ver, efetivamente, com aquilo que são os conceitos da chamada economia circular e, por isso, com novos usos dos materiais, assim como com a forma de usar e preservar os materiais. Não há nada melhor, nem ninguém melhor que possa nos descrever qual a estratégia nacional no contexto europeu da economia circular e, portanto, também do nosso racional para a preservação ambiental e para a transição energética do que o Ministro do Ambiente e da Transição Energética, João Pedro Matos Fernandes, que eu agradeço a participação nesta sessão plenária e que nos vai introduzir o tema do ponto de vista político e técnico e depois seguiremos com um painel de cientistas que abordarão desde aquilo que se passa na Terra, aquilo que pode acontecer nos astros, para melhor percebermos o impacto do conhecimento dos materiais através da tabela periódica naquilo que poderá ser o futuro compromisso entre o desenvolvimento económico e a preservação do ambiente. Muito obrigado.
Muito boa tarde a todas e a todos. Começo por cumprimentar o meu colega e Ministro da Ciência e do Ensino Superior, meu querido amigo Manuel Leitor. Só de facto pela amizade é que já vou no terceiro convite seguido. Tem muita responsabilidade para mim. Acho que nunca ninguém me convidou 3 vezes para nada, desde que sou Ministro. E, portanto, repito, isto é uma responsabilidade acrescida. E ainda por cima tenho melhorado de posto. Comecei por intervir num painel, depois numa sessão diferente, agora numa sessão plenária, uma estreia. Estou quase nervoso. Cumprimento naturalmente todos os promotores, a Fundação para a Ciência e Tecnologia, a Ciência Viva, a sua Presidente aqui presente, os investigadores, e quero começar por dizer que este início de discurso que tenho escrito e que vou ler por economia de tempo vai causar um problema aos intérpretes, mas vou dar o meu melhor. Hoje, ali na cozinha, roubei carapaus fritos. Esta era uma das mnemónicas que eu utilizava para decorar famílias na tabela periódica nos idos tempos do liceu. Era a primeira coluna. Não sei se ainda hoje se usam. Há muitas outras. Uma que eu gostava particularmente. Helena Nervosa armou o crime, cheia de rancor. Os gases nobres. Está-se mesmo a ver. Na altura chamavam-se gases raros. E para celebrar o Ano Internacional da Tabela Periódica, a Unesco associou-se à Associação Europeia de Química para desenhar uma nova versão dessa tabela. Uma que refletisse 2 perguntas fundamentais. Primeira, quanto existe de um dado elemento? Segunda, teremos nós o suficiente em face do uso que dele fazemos? A tabela que surgiu desenhada em nada se parece com a original. Os limites variam consoante a disponibilidade de cada elemento. As cores variam do verde ao vermelho, conforme o risco da escassez aumenta. E para perceber como esse risco é sério, foram sinalizados os elementos que fazem parte de um simples smartphone. Dos 30 elementos sinalizados, 18 têm um fornecimento de limitado a seriamente limitado. 4 elementos são oriundos dos chamados minerais de conflito, associados a locais politicamente instáveis, onde a exploração humana existe, à qual se deve combater a todo custo. A União Europeia também produz uma tabela de elementos críticos para a sua economia. A última versão dessa lista data de 2017 e traça um cenário preocupante. De todos os materiais críticos de que necessita, a Europa só consegue cobrir internamente 9% desses materiais. Tudo o resto é importado do exterior. Um fator ainda mais agravado pelo facto de a recuperação desses materiais por via da reciclagem ser mesmo muito baixo. A respeito da publicação da tabela da Unesco, a Sociedade Europeia de Química disse o seguinte, e cito: como indivíduos, necessitamos de questionar se os upgrades dos nossos telemóveis e de outros aparelhos eletrónicos são realmente necessários e temos que assegurar que reciclamos os resíduos de equipamentos elétricos e eletrónicos corretamente, evitando que vão parar a aterro ou acabem a poluir o meio ambiente. A um nível político, precisamos de ver um maior reconhecimento do risco associado à escassez de um determinado elemento e ter ações fortes para apoiar uma reciclagem de maior qualidade e uma economia circular eficiente. Fim de citação. Minhas caras e meus caros, esta nova tabela periódica cumpre o propósito para a qual foi criada, o de nos conduzir à reflexão e, preferencialmente, à ação. O vice-presidente da Comissão Europeia, Markus Šefčovič, referiu que há um risco real de matérias-primas como o lítio, o cobalto ou o ouro, e se de facto não agirmos depressa e bem, vamos ficar dependentes de fornecedores externos. Mas se há mais ouro numa tonelada de telemóveis, se há mais prata em lamas de água residuais do que numa tonelada de minério bruto, por que é que ainda evitamos olhar para as perdas estruturais do nosso sistema económico? E sim, falo daquele telemóvel que está no fundo da gaveta lá de casa. Estamos perante um risco real de acesso a materiais e produtos, porque é que continua a ser mais barato e conveniente deitar fora e comprar novo do que arranjar? Porque não vemos mais design funcional, a venda de serviços, uma aposta clara na reparação, na remanufatura, ou em novos materiais que não sejam nocivos para o meio ambiente e saúde humanas e que sejam mesmo facilmente regeneráveis? Eu respondo, porque foram 100 anos a produzir linear para os consumidores lineares e com crescimento também linear. E se há 100 anos os limites desse crescimento estavam longe, hoje batemos de frente com eles. A linearidade já não é uma opção, temos de mudar, conscientes de que essa linearidade extrai, transforma, transporta, usa, descarta, não é um qualquer modelo económico, é um modelo económico que resulta da modernidade e que nos trouxe o bem-estar que hoje dispomos. A economia tem agora que ser desenhada de modo a garantir as bases do bem-estar social dentro dos limites que o planeta nos impõe. E neste contexto, a palavra crescer terá de ganhar outro significado, muito para além do financeiro. Descarbonizar não pode ser, afinal, o nosso único objetivo. Temos plena consciência de que alcançar a neutralidade carbónica terá de ir a passos de sistemas de produção e de consumo mais inteligentes que preservem e regenerem, ao invés de extrair e desperdiçar. E que tenham no seu centro o bem-estar social e a valorização do território. Minhas caras e meus caros, o último fogo do Horizonte 2020 está já planeado. Serão 3,7 mil milhões de euros para um futuro de baixo carbono e mais resiliente às alterações climáticas e serão 1.000 milhões de euros para a economia circular. E há poucas dúvidas que o próximo Horizonte, o Horizonte Europa, irá reforçar esta ambição em virtude dos desafios que se colocam ao tecido industrial europeu, aos seus cidadãos e cidadãs e às instituições deste campo em face dos limites impostos pelo sistema natural. E Portugal deve responder à altura, e o Ministério da Ciência, da Tecnologia e do Ensino Superior tomou a iniciativa de promover as agendas temáticas de investigação e inovação, providenciando uma ferramenta importante para que o sistema científico e tecnológico nacional saiba quais as áreas a apostar, que o conhecimento deve ser robustecido, quais as capacidades técnicas a serem incentivadas. As universidades, os institutos politécnicos, os centros tecnológicos, os laboratórios colaborativos, enfim, todo este nosso sistema de investigação e inovação nacional tem que responder a esta chamada. Desde a revisão e reforço dos seus currículos, logo nos primeiros anos da faculdade, até à criação de redes de conhecimento que possam precipitar candidaturas internacionais. A escassez de recursos, a perda de biodiversidade, a poluição, as alterações climáticas são já parte do nosso sistema socioeconómico. Vamos continuar a ignorar as relações que existem entre estas e a desigualdade? Entre estas e os modelos económicos ou o impacto nos sistemas públicos de saúde? Ou devemos nós formar os jovens que agora entram na faculdade para esta realidade? Os novos economistas, os novos designers, os novos engenheiros. Reforçar os cursos técnicos e tecnológicos para a reparação, a atualização, a remanufatura, não só de digitalização ou de modelos de previsão e monitorização, se faz a ciência. Por isso, ao enfrentar desafios globais, as políticas, tais como as atividades económicas, têm de ser como os organismos num ecossistema. Um ecossistema que é suficiente, que é colaborativo, que é mutualista. Essas são as qualidades que tornam uma instituição resiliente e adaptável. Temos obrigatoriamente de começar a incorporar uma visão de missões, tal como é proposto pelo próximo Programa Horizonte Europa da Comissão Europeia, em torno de desafios específicos e ambições concretas a nível nacional, para assim congregar as instituições do sistema científico e tecnológico nacional para o desenvolvimento de soluções. O meu professor de Análise Matemática 1, Nelson Amoeda, ensinou-nos, uma turma inteira, e éramos muitos, a maximização das funções a partir da forma como as folhas se dispõem num pé de uma flor. E dispõem-se de uma maneira muito simples, de forma a maximizar o tempo de sol que cada uma delas recebe, ou, se quiserem, a minimizar a sombra que umas fazem sobre as outras. A natureza, de facto, nunca se enganou. Os sistemas naturais, o conceito do just fit é mesmo um conceito dos sistemas naturais. E nós sabemos bem que esse não é o conceito dos nossos sistemas económicos. É pedido às vezes a um Ministro do Ambiente que seja agnóstico relativamente ao crescimento económico. Eu não sou. E não sou por uma razão muito simples. É se somos hoje 7,2 mil milhões de habitantes na Terra e tudo concorre para que em 2050 sejamos 9,8 mil milhões, a economia tem que crescer. Tem é crescer sendo hipocarbónica e tem que crescer regenerando recursos. Não há outra forma. Mas sim, a economia tem que crescer. Tem é que crescer dentro dos seus limites naturais e por isso eu volto ao conceito de quem nunca se enganou, que é mesmo a natureza quando cria ecossistemas. Nunca se enganou. Os economistas passaram a vida, aliás, reparem, a palavra economia é uma palavra recente, porque mesmo já no tempo da modernidade, a economia era entendida e dizia-se sempre economia política, não se dizia de outra forma. Eram modelos socioeconómicos que naturalmente pretendiam estruturar, para não dizer justificar, não quero ser mau com ninguém, pretendiam estruturar determinadas formas de abordar a maneira como nos organizávamos na sociedade. Depois a palavra política desapareceu do conceito e ficou só economia e tentaram associar e importar para dentro da própria economia as leis da física. Ora, acontece que a economia não tem rigorosamente nada a ver com a física. Para um engenheiro, isto é tudo muito normal, muito banal, muito natural. A extraordinária lei da oferta e da procura, afinal, não é mais que a terceira lei de Newton. Não vale a pena tentar ir mais além. Todos já a conhecíamos. Mas, de facto, a economia não tem mesmo nada a ver com a física. A economia é toda ela termodinâmica. Toda ela termodinâmica. Dentro de um sistema fechado, neste caso o nosso planeta, consomem-se recursos e energia, transferem-se recursos e energia, perdendo energia que temos que voltar a injetar, perdendo recursos que são desperdício. Só que, de facto, é muito mais fácil para os economistas entender as leis da física que as leis da termodinâmica. Estão aqui ilustres académicos da primeira fila que podem, obviamente, fazer esse desafio de ensinar as leis da termodinâmica aos economistas. Eu não caio daí abaixo. Eu já não caio daí abaixo. E é por isso que não vale a pena ser otimista nem ser pessimista. A ideia do otimista que diz que o copo está meio cheio e a ideia do pessimista que diz que o copo está meio vazio, em minha opinião, nenhum dos dois tem razão. Aquilo que nós devemos concluir é que o copo tem o dobro do tamanho necessário para a água que tem lá dentro. E por isso podia ser mais pequeno. E a noção do just fit seria, de facto, aplicada à economia. Muito obrigado.
Boa tarde a todos. Na pessoa do Sr. Ministro Manuel Leitor, cumprimentar todos que estiveram envolvidos nesta organização e por terem escolhido também o tema 150 anos da Tabela Periódica para estarmos aqui a celebrá-los e nesta excelente festa que nós temos da ciência, como a Helena Pereira disse hoje de manhã, logo a abrir os nossos... So, now in English. The General Assembly of the United Nations proclaimed 2019 as the International Year of Periodic Table of Chemical Elements, celebrating the 150th anniversary of the publication of the first periodic table of chemical elements by the chemist Dmitry Mendeleev. The periodic table, besides being an indispensable scientific tool, is generally perceived as an icon of chemistry, reflecting its essence and scientific centrality. The periodic table that we know today, and that we have always at hand, at least the chemists, is an updated version of the table drawn up in 1869 by the Russian Dmitry Mendeleev in the second volume of the book Principles of Chemistry for his students of the University of St. Petersburg. By arranging in rows and columns the 63 elements known at that time in order to highlight the similarities of their chemical properties, he found that they varied periodically with the atomic mass of that chemical element. The periodic table of the Mendeleev did not represent any novelty, since other tables with the same purpose were already known. So, what was the novelty of this periodic table? So, in addition to having empty spaces for the elements not yet known at that moment, the periodic table included the atomic mass of the elements that were not known, but they should exist. Of course, then, after they discovered the gallium, the scandium, germanium, the technetium, and so, over the years, new chemical elements have been discovered. For example, in 2016, the seventh line has 4 new elements, those with the atomic number of 113, 15, 17, and 19, which have named in Portuguese Nipônio, Moscóvio, Tenécio, e Organésian. So the periodic table that we use today are organized by the atomic number and not by the atomic mass. And the explanation of its properties is based on its electronic configurations, something that come to be discovered later. So, as Professor Jorge Calado wrote in the public newspaper in February 16, 2019, the common citizen, or street man, or the society in general will ask, how important is this? To the point that UNESCO dedicates a full year to it. Now I will be provocative. The answer is, chemistry is the central science. It feeds on physics and explains biology and many of the biological phenomena that exist in our organism, both in its normal functioning and in disease situation. Everything that exists, humanity included, is made of chemicals and in constant interaction and reaction. Without chemistry, life would not exist. Physics does not arrive. The major obstacle to the rationalization of chemistry lies in the diversity and mutability of substances. So now we'll pass to the gentlemen and to Zita to learn a little bit more. And because I will say lady, but it will be better to say the name, yeah. And we will start by David Hamilton. David, it was the president of the European Chemical Society. Now it's the past president or vice president. He's also a retired professor of chemistry of St. Andrews University, and spent quite a lot of time to joke, let's say, about chemistry and saying very, very interesting things about our periodic table. Please, David.
Okay, so good afternoon, everybody. Welcome to this session. So I'm going to be talking about astrobiology, the origin, evolution, and detection of life in our solar system. And this is in this session because one of the big questions in science, in fact, is how do we move from having simple organic molecules to having the basic unit of life, which is the cell. So this is one of the big questions in science, and in particular, it is a big question in astrobiology. So, and I'm an astrobiologist, and this is exactly what we do, is try to understand this question. So there are different theories about this. How do you jump from organic molecules to having life? One of them, it says that the exogenous delivery of the organic molecules allowed this to happen. So we know that since the solar system was formed, and our Earth, that is roughly at 4.6 billion years ago, until roughly 3.8 billion years ago, there was heavy bombardment by comets, meteorites, and asteroids. And that's exactly what I'm going to show you. I'm going to show you in this talk that the comets and the asteroids and the meteorites are full of organic molecules that played a role in the origin of life here on Earth. So let's start by meteorites. So I brought you some photos of meteorites. What they have in common, all of them, is that they're full of, well, they have iron and nickel. That's one of the typical things of a meteorite, so all of them. This one on top here is just a big piece of iron. It's called an iron meteorite. But in my case, as a chemist, I'm not particularly interested in this one, because as you can imagine, all the organic molecules were burned out and they're not there anymore. So I'm particularly interested in this sort of meteorites here. They're called carbonaceous chondrites. As the name indicates, they're very rich in carbon. And indeed, all the organic molecules that are present in this meteorite have been preserved since the solar system was formed. So by analyzing this sort of samples, I'm not only seeing the chemical conditions that happened by the time that the solar system was formed, but I'm also seeing the typical organic molecules that were delivered to the Earth just before life originated. So one of the molecules we're particularly interested in is water. So one of the big questions was always in this field was, how did we get the water we have here on Earth, the water we have in the oceans and rivers and lakes, etc.? And for many, many years, scientists believed that comets, and I'm going to talk about that in a couple of minutes, scientists believed that comets were the ones bringing all the water. Why? Because comets are also known as dirty snowballs. So if you think about ice being brought to the Earth, arriving here on the Earth, melting, and then we would have the oceans. This is all very fine, but as we know in science, if you have a theory, you have to go to the lab and you have to prove it. So what scientists did was actually to measure the deuterium versus hydrogen, which is here, ratio of water in different bodies. So they measured that in the Earth, the water present in the Earth. So it's here, it's this value. And then they did that for different comets. And you see here all the different comets, the ones from the Oort cloud, the ones from the Jupiter family, etc. The main thing you have to retain here in this figure is that the values, the DH ratio, it doesn't fit well with the one from the Earth. So that puts to rest the theory that comets were the ones bringing the water to the Earth. Alternatively, scientists measure the D over H ratio in carbonaceous chondrites, the meteorites I just talked to you about, and actually they fit perfectly. So this was a study very recent, in 2012, and now this study is from 2014. Finally, scientists discovered that the water we have in the oceans today is actually from asteroids, and in this case, from meteorites. So here you are, here. But we have more organic molecules than just water in carbonaceous meteorites. We also have amino acids and nucleobases and carboxylic acids and sugars and phosphoric acid, etc. A huge list. So what we do as chemists in the lab, because I'm a chemist, is actually to use pure chemistry, but instead of analyzing a normal sample, as we say, we analyze meteorite samples. So I'm bringing you here a GC TOF-MS. This is all very technical, but this is just to show you how chemistry can be applied, and it is applied to extraterrestrial samples. So each one of these peaks corresponds to an amino acid. And so it is possible to say, without a doubt, which organic molecules are present in a meteorite. And in addition to that, and you may be wondering, these organic molecules are all extraterrestrial, so they're all formed outside of the Earth. And again, chemistry plays a role. I can distinguish clearly if a molecule was synthesized here on the Earth by a microorganism or by any other biology, or if they were synthesized outside of the Earth. So chemistry allows us to distinguish that. But so it is great that we have meteorite samples to study the chemistry and tell us about the chemistry of the early solar system. But we always think that the meteorites, as soon as they arrive here on the Earth, they get contaminated. And so we need to find alternatives. We need to find samples that are more pristine, that are not contaminated. And in that case, we plan space missions. So we know that the meteorites come from this place. It's called the asteroid belt. It is located between Mars and Jupiter, and so scientists plan space missions to the asteroid belt. I'm bringing you here a real image taken last year. This is from the Yabusa 2 space mission. This is a mission from the Japanese Space Agency. And what's happening right now as I speak is that the mission is analyzing this asteroid, which is called Ryugu. What's happening in December of this year is that the mission is going to collect samples and start its journey back to the Earth. So next year, the samples will arrive in Japan, and all the colleagues from this mission will analyze those samples. I'm very lucky because despite the fact this is a Japanese mission, I'm invited and I'm a scientist in this mission, so I'm very happy to say that hopefully next year I'll be in Japan analyzing and contributing to the chemical analysis of this sample. But not only we visit asteroids and we analyze meteorites, we also have been visited by comets. And I'm bringing you here a tapestry from the 11th century. And if you look here, this is no star. This is Comet Halley, that since the 11th century, at least, has been visiting us constantly. And again, if it's not the comet visiting us, we go, a scientific community, and we go and we visit the comet. Here we have real image from this comet called 67P, also known as Churyumov-Gerasimenko. And this is a mission from the European Space Agency. So as Europeans, we're very proud when we have a space mission that it is successful. So many analyses were performed, and among them, we also analyzed the chemistry of this comet. And so the PI of this space mission, Catherine Altweg, which was the PI of the Rosina instrument, she said that this comet had the perfume is quite strong with the odor of rotten eggs due to the presence of hydrogen sulfide, horse stable due to the ammonia, and the pungent suffocated odor of formaldehyde. This is mixed with the faint, bitter, almond-like aroma of hydrogen cyanide. And it keeps on. I can tell you that a couple of years ago, I was still living in London, and I was being funded by the Royal Society, and they funded what they call the summer exhibition, where all the scientific community goes and presents their data, and the families and the children, everybody goes and visits and see what the scientists are doing. And scientists from this mission, they printed these postcards, and on the other side, they sprayed it with this mixture of chemicals, and they're giving away the postcards. I smelled the postcard. It was disgusting. But at least I can say I know what a comet smells like. So in terms of the chemistry, the problem with this sort of analysis is that, for example, this comet already entered the inner solar system. And as soon as a comet enters the inner solar system, the ice melts or sublimates. So it is processed. So the chemistry I'm seeing here is not the chemistry of the primitive, of the early solar system. So alternatively, there's a mission that it was just accepted by the European Space Agency. It's called Comet Interceptor. It's going to be launched in 2028 together with the Ariel space mission, so we're very happy with that. And I can say that it is with great honor that I'm saying that I'm part of this mission, so Portugal is going to be represented. And in 2028, well, not 2028 because it's the launch, but after that, we will be able to tell the chemistry of this comet. So I've shown you the possibilities how life originated here on the Earth, but there are other places in our solar system that may also have the necessary chemistry for life to develop. One of them is Mars. This is a real image taken by the Viking mission in 1976. In 1976, this mission didn't detect any organic molecules, but scientists didn't give up, because the problem with this mission is that it had technical problems and they were looking on the wrong location. Since then, scientists have detected methane on the atmosphere of Mars. And this is very strange, because methane is not expected to survive on Mars. In fact, methane, when it's hit by the radiation on Mars, it easily decomposes into formaldehyde, methanol, and carbon dioxide. So if the scientists are seeing constantly methane in the atmosphere of Mars, that means there is a constant source inputting the methane into the atmosphere. So there are two possibilities. Possibility number one is not very exciting. It's a geological reaction between a rock called olivine and water and CO2, and that releases methane. That's not exciting at all. The option number two, that's very exciting, because we may have some microorganisms called methanogenics releasing methane into the atmosphere. There's currently a mission, part one of the ExoMars mission. It is the TGO. It is an orbiter that is going around and around. There's lots of discussion at the moment. Some people say that that mission didn't see a thing, but other researchers from other missions, they say that they continuously see the methane. So the scientific community is discussing a lot about that. Moving on, other places in our solar system that may have the right chemistry and harbor life. This is a photo from Enceladus. This is a moon from Saturn. This is a real image taken by the Cassini mission. And as you can see, the surface is icy. So you may think, okay, this is icy, what's the point? If the moon is all icy, no life forms may exist here. But the truth is, if you see these fractures here, it means that there is something forcing the ice to break. And that thing is an ocean of liquid water. And where there is liquid water, there is the hope, at least, that there are forms of life. So again, this is a real image. What you see here are no lights. Those are plumes, geysers coming out of this moon. And in fact, even though the Cassini mission was not prepared to detect life in this moon, it had the right chemistry equipment to detect some organic molecules. One of the organic molecules that was detected was methane. Here it is, methane surrounded by water. And again, the same thing. Where there is methane, there is hope that there are forms of life. So we're waiting for space missions, both from the European Space Agency and NASA. And hopefully the next few years we'll have a mission there, and hopefully, fingers crossed, saying that there is life in this moon. The future, well, there is, NASA just announced last week that they will have a mission in 2026 to another moon called Titan. Titan is a moon of Saturn. The funny thing and interesting thing about this moon, it doesn't have any water, liquid water. All you see here, obviously this is a drawing, this is not a real image, but what you see here are lakes of hydrocarbons. And there is a huge interest in different industries to analyze and extract those hydrocarbon lakes and oceans. So this Dragonfly mission is actually a life detection mission. We're able to say if there is life on Titan or not. So to wrap up, we actually don't know if there is alien life in other parts of the solar system, meaning we don't know if life originated in other parts of our solar system, let alone in other solar systems. We'll have future space missions, as you've seen this morning. We'll have the IDL space mission that will look to among other things, to the atmosphere of exoplanets, but we'll see. At least in our solar system, we're not sure if we'll have life or not. What we know is that the chemistry in many locations, such Mars, Enceladus, Titan, Europa, which is another moon, it has the right chemistry. So all the right conditions to life to flourish are there. What we have to do is explore and be really, really patient that we'll be successful in the next few years. Thank you.
Thank you, Zita, for this excellent talk about organic chemistry in the moon at least. So now I will try once again to have David to have the new periodic table by contrast with mine.
Hi, it's me again. Sorry. I'm really, really sad that I have to come after Zita, because that was a fantastic lecture, and I can't do any better than that, so it's really superb. Okay, so I'm going to talk about I was going to give the introduction to the speakers and to the periodic table, but I'm going, in fact, to talk about the new periodic table, which you have already heard about in Portuguese, and I don't have much to add to what the minister said. But I particularly want to thank the people who were involved. This was the new periodic table was developed by a team from the European Chemical Society. Their names are here. Oh, no, that's not right. Sorry, their names are here. And I particularly want to mention Nicola Armaroli, because he had an enormous influence and has, in fact, had this put in every school in Italy and has done a roadshow to some tens of thousands of school pupils. But I especially want to thank Suzanne Issa here, who works in the reprographics department in St Andrews, because she is the person who actually drew the thing, with me sitting there saying, move this line there, move that line there, put this color there, put that color there. So she's really behind it. The periodic table, you probably remember it from when you were at school, and it looked something like this, not quite like this. This is a rather unusual version of it, but that's the modern periodic table that we look at. This is a different one in that it's made of macrame, which is an ancient knot tying craft. It was done by Jane Stewart, and it involves 200,000 knots, and this was done specifically for the International Year of the Periodic Table. And it's a really superb thing. But when you think about the periodic table, if you're not a chemist, you may think, well, it was that kind of thing on the wall, it was coming off, it wasn't very interesting, not much to it. To a chemist, it's the most wonderful tool to be able to predict everything. And so when we thought about the fact that most non-chemists don't really understand it, we thought, let's make a new one which will have a message which really makes people understand it. And this is what we came up with. And really the most important thing here is this. If you read this, the 90 natural elements that make up everything. Just think about that for a moment. There are only 90 building blocks of everything in the world. I would say everything in the universe, but I've been hearing all about neutron stars this morning, and they're not made up of elements, but everything else is made up of elements. It's astonishing, only 90. And if there are only 90, we really have to look after them. And that's what we haven't really been doing, and that's what this message is doing. So the periodic table, as you notice here, is not the same shape as the one I showed you just now. It's completely different. And it's different because the area occupied by any one of these elements is proportional to its amount in the Earth's crust and in the atmosphere on a logarithmic scale. And so we have lots of oxygen and we have much less of the ones down here. Then we've color-coded it, and we've color-coded it to show that the ones that are red, if we go on using them, they will be dispersed within less than 100 years in such a way that we won't be able to get hold of them. Now, I would say they'll be lost. They won't be lost. They'll all be here except one, which I'll come back to later on. They'll all be here, but they just won't be able to be got hold of. And then the orange is a bit longer timescale, and the yellow depends on increasing use. And then you'll notice there's a smartphone signal on 30 of these elements. These are the 30 elements in a mobile phone. And you see many of these are red, which means that they're likely to run out within the next 100 years. And then we have 4 elements here which are black. These are from conflict minerals, which they don't only come from these places, but they can come from countries where people fight wars over the mineral rights, or they fund wars with the proceeds of the mining. And so we have to be very careful about these 4, tantalum, tungsten, gold, and tin, and how we use them. And so I'm going to have to take this off. I'm going to talk about some of these elements now, but I'm going to take that off there. But so that you can see it all the time, I'll just show you a different version of it. So I just need to be able to point to it later on so you can see. So here we have Right, so let me talk now a bit more about mobile phones, about smartphones. I promise you I'm not going to take anything more off. Right. So let's talk about smartphones. They're the absolute archetypal example of a use and discard object. You use your smartphone, you make calls with it, and you suddenly decide you want to change it. And look at this number here. In the European Union, we upgrade 10 million phones every month. Just think of that, 10 million a month. A month! It's incredible. And what do we do with them when we hand them in? Well, sometimes we hand them in, and if we do that, they get taken usually to developing countries where they can be used for a bit, then they're trashed, and very often they're mined for some of the metals, particularly gold, under appalling conditions, often by children, often in the street, and the final resting place of the phone is in some kind of landfill site or even just in heaps on the side of the road. We don't have a good way of dealing with them if they're handed in, but almost all of them don't get handed in. How many of you have in your drawer at home a phone that you don't use anymore? I bet almost everybody has a phone at home which they don't use. And so those elements in that phone which you've got in your drawer cannot be used by anybody. No one's going to come in with some kind of digger and take the elements out of it. So they're not available like that way. So the other thing is, it's very difficult to repair a mobile phone because the companies who make them make sure you can't, so you have to have a new one. So we need to have modular phones where we can repair the phone. Now, when you know all of this, I just mentioned two elements here. Indium, which is used in touch screens, indium tin oxide, is in every touch screen, only 20 years of it left in the form that it is, in available form it is at the moment. Tantalum, which is a conflict mineral and is used in microcapacitors. There's one microcapacitor in every iPhone, and iPhones have 43% of the market, so there's a huge number of them, less than 50 years left. And this is a conflict mineral. So what phone companies do actually is they trace where the element comes from. They trace it from the mine through the manufacturing to the phone to make sure they aren't using them from these mines, which are usually in the Democratic Republic of the Congo. But they will, as it gets more expensive, they will be tempted to use the tantalum. So knowing all of that, you change your phone probably every 2 or 3 years. Can you justify that? Wouldn't it be better to hold on to it for a bit longer so we can save these elements and look after them properly? So what we need to do is we need to recycle what we have in the phones. Now, we need to have a proper way of doing it. And one of the problems is we don't really have this. We have it on a small scale, but we need to have this on a large scale, the ability to recycle. When we have that, we need to have incentives to hand in the electronic devices. And it's not just phones, of course, it's also computers and everything else. We have to recycle. So we have to try and get the indium tin oxide out of every computer and the tantalum. And this is the circular economy. We have to try and develop the circular economy, which has been mentioned before already. We also have to try to replace these elements like indium with ones which are earth abundant. So graphene, there was a very good lecture about graphene this afternoon. This is a possible replacement for the smart screens, but none of these are yet at the stage where they can be used, and it requires a huge amount of research effort. So let me just repeat. Change your phone less often, and when you do change it, hand it in. And what about this recycling? Well, here's the periodic table again, which I've changed slightly, and the pink is the thing to concentrate on here. That means that we're doing recycling less than 1% of the elements. And if we look at indium, which is there, you see that it's less than 1%. We look at tantalum, it's here, it's less than 1%. If you look at platinum and rhodium, which are used in exhaust catalysts, they're not red in this periodic table. They're orange, and they're not red because they are being recycled more than 50%. So recycling is possible, and it has to be done. One little other story, if I may, about helium. Helium is a very interesting compound, and I'll show you here is this one up here, the red one. So I need to have my T-shirt. It's very light, and its main use is in cooling the magnets in MRI images. Another major use is in diving, where you dilute oxygen with helium so that you don't get nitrogen narcosis, which is a problem if you have nitrogen because it dissolves in the tissues and the blood, comes out as bubbles and you die. Oh, yes, just finished, nearly finished. But once released in the atmosphere, helium can be lost forever. It's very, very light, very stable, goes up to the outer atmosphere and escapes forever. This is the one element we can lose. And in these two applications, helium is recycled. There's a chap diving with a helium recycling unit. Here's a helium recycling unit for an MRI scanner. But look at this. Currently, the only operating plant for helium is in the United States, and it's going to close in 2021. There was one in Qatar, it's closed already. Tanzania is about to open one in 2020, and it has enough, if we only use this stuff once and don't recycle it, for only 8 to 12 years. So the question is, can you really justify having helium in your party balloons? It's a really precious resource, and I was pleased to see the demonstration this morning. They used blown-up balloons, not helium balloons, so well done, you guys. It will be lost forever. When I said this, I've had a lot of flack from the balloon industry, and they gave me the information I needed, which is, first of all, they say they use 10% of helium in balloons. It's 47% in Russia. They use dirty helium. It can't be reliquefied. But actually, if you find out what it is, it's 95% helium, and what they're going to take out of the Tanzanian field is less than 10%. So it's much easier, although the economy of scale is not the same, to recycle this helium and not put it into the balloons to send them up into the air. And this means that if you use 10% in party balloons, and there's only 8 years' supply, it will all be gone in less than 100 years. It's really shocking. Please don't use helium balloons. There we are, I'd say it again. Okay, and in Gibraltar, they used to have a national day, just down the bottom here, where they released thousands of balloons, helium balloons. They've now been banned, partly actually because of the plastic which goes into the sea, gets swallowed by whales, and they die. So let me just finish with one comment. Why can you never trust an element? Because they make up absolutely everything. Obrigado. And before I go, I would like to present the Minister, if I may, with a copy of the periodic table, especially in Portuguese for you, sir. Is the British ambassador here? No. Okay.
Thank you, David, for this excellent talk about the new periodic table and the concern that we must have about the elements. Well, as president of the Portuguese Chemical Society, I can say that the Portuguese Chemical Society is associated with the celebration of the International Year of the Periodic Table, and we are distributing these T-shirts to try to convince the young generation that we must think about this circular economy and these elements. So the next speaker, it will be James Durant. He is a professor of the Faculty of Natural Science, Department of Chemistry of the Imperial College. And what I can say is two sentences. Is development of renewable, low-cost energy technologies is a key scientific challenge for the 21st century. James' group primary research interest is the development of new chemical approaches to solar energy conversion, harnessing solar energy either to produce electricity or molecular fuels. And I think it will be the discussion in his presentation. Please, James.
Thank you very much for that kind introduction, and thank you, Zita, for inviting me to talk this afternoon and bringing me to beautiful Lisbon. Though I must say I'm a bit daunted for two reasons. First of all, of course, to follow those two beautiful talks, I've heard I don't have so many beautiful photos and images, and I'm going to keep my clothes on. So I'm not going to be quite so exciting. I'm also a little daunted because, of course, I'm coming from the UK, which is not one of the most sunny countries in the world, and I'm coming to Portugal, which, of course, is blessed by rather more sunshine than we have. but I do want to talk to you about some of our own thoughts about the challenge of harnessing sunlight and thinking about how new materials and new elements can contribute to the development of new technologies for harnessing sunlight. I'm going to be talking both about the challenge of making electricity with sunlight, so the idea of solar cells. I'll be talking also about the challenge of trying to make fuel, and I'll connect that as I go along to the wonderful elements which we heard about from David so eloquently. When we think about how we can harness sunlight using excitations, then of electronic excitations, then of course, by far the most established way of doing that are plants. Plants have, over the millennia, worked out how to harness sunlight to make the biomass, which of course is the origin of the oxygen we breathe and the food we eat. And that, of course, for me, plant photosynthesis is the inspiration for almost all of my science. We also now know very well how we can shine light onto silicon solar cells and make electrons and holes and make current and use that to drive a light or to drive our computer or whatever else we want to do with electricity. I'll talk a little bit about solar cells and how we can learn from plants to make new sorts of solar cells. And then I'll talk at the end about the challenge of directly learning from plants and trying to achieve artificial photosynthesis, trying to develop materials which can harness sunlight to make fuel. On one level, of course, photovoltaics or solar cells is a success story. If you look at all the trajectories of what's happening globally, then the growth of solar or photovoltaics, of panels like this, is stunning. This was my son outside his school in London some 20 years ago when they installed solar-powered parking meters in London, which the local council liked, and I got very excited about because that was my first demonstration of solar in the UK. Of course, that's a rather smaller, a rather modest scale. My son is now taller than me, and these are the solar panels of the solar fields in the UK. The growth has been stunning, and I think whatever the politicians do, and of course some politicians, particularly I'm thinking of the US at present, are maybe not so keen on some renewables as others, but the growth of solar, I think, is now unstoppable. There are now many parts of the world where if you want to generate electricity, the cheapest way to do that is by installing photovoltaics. It's cheaper than installing fossil fuel-driven power stations. And that has all been driven by the development of silicon solar cells. And of course, that is fantastic. And that has gone, the cost of that technology has plummeted over the last 40 years, and that's what's driving the cost. It also means now that much of the cost of a solar system is no longer the solar cell, but the land you use and how you put it up and what you hold it with. But of course, if I walk around London or I walk around Lisbon, then it's not covered in solar cells. And one of the challenges is that a silicon solar cell essentially comes in one form. It comes in between two glass plates, it's heavy, it's black, and if you want to put it on a building, you stick it on top of a roof, you don't typically make it the roof. And that, of course, means that it's not very integratable into much of our living world. And what I personally am very excited about is can we develop new technologies, new materials, which enable us to integrate photovoltaics, devices which convert sunlight into electricity, into our environment, or into our cars, or into our planes, in ways which enable us to do things which we can't do currently with silicon. Here's examples from my colleagues in Swansea, in South Wales, where they're putting up buildings. South Wales is pretty much the wettest part of the UK. There isn't much sunlight in South Wales. These buildings are off-grid, solar-powered, not only powering themselves, but powering electric cars with the excess energy from the solar panels on their roof. And they were erected with no silicon. There's no silicon solar cell in those buildings. They use a flexible copper, indium, gallium diselenide, and you'll see the theme of the elements. By using more elements, they've been able to make a device where the device is flexible. You can laminate it onto a steel roof, so you can put up a building which isn't strong enough to hold up silicon. The reason why you don't have silicon panels on warehouses It's because they're too heavy. If you want to put silicon panels onto a lightweight steel building, you need a lightweight product. That's a lightweight product. David will point out there's indium in it. That's not a good idea as a scalable product, but it's a place to start. You also have a challenge that, as we already are finding in the UK, as we rely increasingly upon photovoltaics, then the challenge of storage becomes a big issue, because the intermittency of sunlight means that very often when the sun goes down, then the power goes down. And so our ability to store, develop pathways not only to integrate photovoltaics into a building or into whatever else structure you want, but also to think about ways to integrate into the system where you actually store the energy from the sunlight. And one example here is by trying to couple photovoltaics and electrolysis. And I'll give you more examples of that. What I find exciting in terms of materials is that we're learning how we can print semiconductors. We're learning how we can print materials which can convert sunlight into electricity, essentially using printing technology. So that's a printed flexible solar cell on a metal foil. It has the properties which are very different to silicon. Silicon's a crystal. If you bend silicon, it cracks. That's not good for the device. These are printed, what are often called plastic semiconductors, so that's not the best, the trendiest word anymore, where essentially you print a flexible semiconductor onto a substrate, which allows you to think about making solar cells, which can be lightweight, flexible, potentially translucent, and enable you to think about applications you can't achieve with silicon. What you can also see here is that there are many different ways you can make these devices. One way is organic solar cells. We heard from Zita about organics. These are rather more complicated organic molecules than methane, and I'll talk about why that is in a minute. This is an example of a new solution processed a hybrid material, half organic, half inorganic. What you can see immediately from the fact that this is such a long chemical equation and that structure is so complicated, but it's not so easy, actually, to find the right materials and structures which can convert sunlight to electricity. But we are doing it, and we are finding how we can find materials which can convert sunlight to electricity at efficiencies which are not so different from silicon. This is just one example of what the chemists have been doing in this field, which is not developing so much new elements or using new elements, it's rearranging elements. One of the most widely used electron acceptors in so-called organic solar cells is fullerene, Buckminster fullerene, one of the classic materials which people get excited about in space. That's a wonderful electron acceptor, but actually it's quite hard to synthesize, and it's not very flexible, essentially, when you've got a buckyball, and you can't do much with it as a chemist. This is a rather more complicated molecule. It's a more linear molecule, but this is the sort of molecule chemists love because they can do chemistry on it. And what that has been doing is making molecules like this has allowed us to make a whole series of molecules with different properties and therefore tune performance and so get us to higher efficiencies. It also allows us to do things like this. This was a graveyard of materials which my group had studied as organic solar cells, and you can see the full spectrum of colours you can make with molecules like this. These are all devices which didn't work so well in the solar cell. The other challenge is trying to make sunlight into fuel. And of course, the challenge here is both, in some ways, with electrical power generation, we're tackling the low-hanging fruit. We know now that we are going to be able to move towards an energy economy where we no longer use fossil fuels to generate our electricity, with wind and with solar, maybe with nuclear if you like it, with wind power, with wave power. But what's more challenging is how we can decarbonize transport and heat. And of course, electric cars are part of this, but particularly for planes, particularly for long-distance lorries, particularly for shipping, then we're going to need fuel. And we're going to need fuel for heating as well. And so there's a real challenge around how we can develop sustainable carbon-neutral fuels, how we can store solar energy. And of course, one of the most elegant ways of storing solar energy is in the chemical bond of a molecule. And the opportunity we can think about for trying to provide markets for utilising CO2 rather than simply storing CO2 under the ground. These are the challenges of green hydrogen, or the challenges of liquid sunshine. Of course, there's a huge challenge, but where the sun is not always where the market is. and we have to find ways to transport renewable energy around a planet. And most likely that's not going to be in the form of electrons flowing down cables. It's probably going to be in tankers. And if we're going to transport renewable energy in tankers, we've got to turn that renewable resource, the sun, into something which we can transport as a fuel. There are many pathways by which we can already convert sunlight to a molecular fuel. For example, we can have a solar cell that can generate electrons which can electrolyze water to hydrogen. We can use hydrogen to reduce CO2 to make a hydrocarbon-based fuel. We can already do it. The problem is that if we make a hydrocarbon-based fuel currently, then the cost of that fuel is far higher than digging the fossil fuel out of the ground. And what we have to find are ways to go from sunlight, water and CO2 through to hydrogen or through to a fuel which can become cheaper, or at least start to become cost competitive with fossil fuel power generation. That's a significant scientific challenge. I'm particularly interested in the two areas: can we split water with sunlight, or can we directly reduce CO2 with sunlight? These are both obvious, interesting technological challenges, but also very large scientific challenges. In this field, there's almost as many pathways to try to achieve such a process. We often call this process artificial photosynthesis and artificial leaves. There are almost as many different ways of doing this as there are scientists working in the field. You can think about nanoparticle suspensions where you shine light on and directly split water into hydrogen and oxygen. You can make photoelectrodes and do the same thing. Or you can put catalysts onto solar cells. These are all different ways you could imagine of coupling sunlight to some sort of reaction which makes fuel. There are many different materials which are interesting for this, and these go from dye-sensitized systems. I like rust, actually, but a lot of my research is with Michael Gratzel from EPFL, where we look at nanostructured rust. It turns out if you nanostructure rust, it's actually rather good at oxidizing water in the presence of sunlight. And there's a lot of catalysis. This is both molecular catalysts and inorganic catalysts. And you can see already the range of elements which are required to try and achieve those sort of reactions. Now, I don't normally talk about the periodic table. You very beautifully introduced it. But after I had this lecture invitation, I asked my group what elements they were currently using in the lab in order to achieve either the solar cells or the solar fuels. And the answer was nearly all of the ones which David highlighted. Out of those 90 elements which are widely available, I guess probably 70 of them are ones which are currently in use in my group, testing new materials to try to achieve these challenges of either integratable solar cells, materials you can process over large areas, or trying to achieve the challenge of sunlight to fuel conversion. Some of those materials are rarer than others, and of course one of the challenges is to achieve something which it doesn't use rare elements, doesn't use toxic elements, and doesn't use high-cost elements. None of that's easy when you want to have something which is very cheap and efficient. The last part of my talk, I'll just touch on some of my science. I find my inspiration is how plants convert sunlight to fuel. And this is how a plant does it. Inside a reaction center, a photon comes in and it separates electrons on holes across a membrane to drive electrons this side, and it oxidizes a manganese cluster on the other side. The efficiency is wonderful. Plants are fantastic at harnessing sunlight to chemical energy. The efficiency is equivalent to a silicon solar cell, 20% or so. Depends on how you add the numbers up. But of course, plants did not evolve to meet our needs. And as an organism level, their efficiencies are far lower. But at a molecular scale, they're an inspiration. And what they are doing essentially is taking short-lived excited states, which you make in a chlorophyll, and coupling that to the long-term timescales of catalysis. Trying to split water. Water, everyone knows, is stable. Yep? But water is not useful as an energy element. You split water into hydrogen and oxygen. You can then convert that hydrogen and oxygen back again to water when you burn it, the hydrogen being the fuel. But that's hard chemistry. That chemistry is slow. In a plant, it takes milliseconds to seconds to oxidize water into oxygen. In order to drive this slow chemistry, you've got to turn short-lived excited states into long-lived charges. Plants use around half the energy they absorb from the sun to gain the lifetime to drive the catalysis. So the energy with excited states is about twice the energy which it actually uses to drive the chemistry. And that's just because it needs to gain lifetime to drive catalysis. And essentially, I spend my life trying to work out in many different materials how to gain lifetime to drive useful reactions, be it either electricity or making fuels with new materials. And there's some examples: dye-sensitized solar cells, organic solar cells, that's water splitting. Essentially, in every case, you find the initial state is short-lived, the catalysis or the reaction is long, and it costs energy to gain the lifetime. I don't know how, I've got to finish. I'm just going to finish. I'll skip the last couple of points about my talk, and I'll finish with some acknowledgements to thank all the people involved in the work. I hope I've given you some thoughts of the excitement and challenge, and the idea, and also maybe the idea that in terms of science, the challenge of developing new materials and harnessing new elements is certainly exciting me in our pathways to a more sustainable future. Thank you.
Thank you very much, James, for this excellent talk. Well, the last speaker, it will be Tito Trindade from the University of Aveiro, and I will say two sentences once again to define Tito. Is synthesis, characterization, and surface modification of nanomaterials. And the second one, it is inorganic nanoparticles to produce composite materials with potential interest in bioapplications, environmental remediation processes, and chemical analysis and energy sustainable technologies. And the provocative title is From Old to New. Tito.
Obrigado, Arthur. Antes de mais, muito boa tarde. Muito obrigado a todos os que organizaram esta festa de ciência, que tem vindo a melhorar de ano para ano. É uma oportunidade excelente para nós ouvirmos ciência de outros domínios para além do nosso. É muito interessante. Agora vou mudar para inglês. So, the title of my talk is From Old to New, and you can understand this as a quick tour to nanomaterials research via circular economy concept. Well, this quick tour to nanomaterials research, the point is to show you how we can not only use elements to produce useful products, for example, biomarkers to be used in medicine, but also that we have to introduce in these concerns on development of new materials, also the preoccupation of reusing the products, recycling the products. So I'll start with this periodic table. This is a unique periodic table. It was built by the students of the chemistry department of the University of Aveiro. They have designed it. They have printed a giant periodic table, and is currently in exhibition in our lecture theater. And I'm showing this periodic table to highlight the elements that I would like to talk about in this lecture. These are the elements, the rare earth elements, so which is scandium, yttrium, and then the lanthanide series. The atomic number varies, scandium 21, yttrium 39, and then the lanthanides that goes from 57 to 71. So usually you don't observe the periodic table in this way. These elements present to the F block, so it's usually displaced a little bit to the bottom, but you can also read it in this way. So I've started with this pedagogical and scientific tool, and I'll continue in the pedagogical component because we can use very simple experiments to demonstrate the usefulness and the properties of chemical elements. For the chemists present in this lecture room, I'm quite sure they recognize these images. These images were collected from a website from Stefan Quer, and they demonstrate what is a chemical garden. So a chemical garden are very simple experiments that we use to show, for example, to high school students the simple complex phenomena in very simple terms. Namely, precipitation process, the color of materials that arise for certain elements that we incorporate in those materials. For example, what you have here is a chemical garden made of a silicate, in this particular case of copper ions that are introduced in the network of the silicate and provides this beautiful blue color. In fact, this is not only beautiful and useful from a pedagogical terms, it's very important, for example, to explain, according to some theories, the origin of life. In fact, from chemical gardens to chemobryonics is the title of a cost action that we are involved, and among other things, try to place the possibility that the formation of hydrothermal vents could be in the origin of life. So, but my idea to show you these chemical gardens is that you can do the same with lanthanides. And I've asked a researcher of my group, Claudia, to perform chemical gardens using lanthanides. We didn't find anything in the literature. It's quite interesting. Probably it's a funny thing, but we have made an exhaustive search and we didn't find anything about it. Probably because one of the reasons is that for observing the interesting color of these elements, you have to search for luminescence, photoluminescence. So these photos that you are observing here are chemical gardens, so metal silicates, in this case doped with europium, which is one lanthanide, and in this case doped with terbium, which is another lanthanide. And when you shine these materials with UV light, the photoluminescent behavior comes out and you observe this type of colors. So it's this phenomenon that we have been interested for a long time ago, at least 10 years, in developing nanomaterials that show these photoluminescent properties and can be useful, for example, to biotagging biological systems, such as cells. So the idea, and I'm just showing this as an example of a compound, the idea is to produce nanoparticles, nano-sized particles, so typically about 100 nanometers size range. And in this case, we have introduced this lanthanide compound. Here it's a europium compound. I will not go in detail on the structural and chemical composition. I can discuss it later if you are interested. But this compound shows photoluminescent properties. It shows that pink reddish color that I've shown you before. And so the idea is to introduce this lanthanide in water oil microemulsions, promote a chemical reaction in the presence of a silica precursor, and in that way produce the encapsulation, the nano-encapsulation of the lanthanide compound by silica shells. So for that we use the concept of nanoreactors, which are basically, in this case, micelles in which the chemical reaction occurs inside of the micelle. And so the size of the particle is constrained by the size of the droplet. So this works very nice for a number of compounds, for a number of lanthanide compounds. And what I'm showing here is a transmission electron microscopy image of one of such compounds. So this dark region here on the center of the core is composed of mainly of the lanthanide compound, and surrounding it, what you are observing are the amorphous silica shells that coat the lanthanide compound. So the idea, as I said, is to explore this as biotags. There's a lot of coordination chemistry involved here. When we shine, for example, with UV light of this wavelength, 254 nanometers, what we got is this for this type of nanostructures. This is a false color. It means that the color that you are observing here is due to the UV light, okay? In fact, it's colorless, let's say. And of course, when you shine with the 360 nanometers, you don't see anything at all, only for a shorter wavelength. The idea is to shift the excitation source to visible, because we want to use them as biotags and using conventional microscopy techniques for monitoring biological systems and biological processes. So what we are doing is the attachment of organic compounds to the lanthanide compound in order to act as antenna. So they harvest photons from the solar from the visible spectrum and then transfer the energy to the metal center, and in that way we have luminescence that we are looking for. So this is one of the results we have got so far. Yeah, I would say it's a partial success. Of course, we are trying harder to get shift even more pronounced to the visible range, but it's okay. When you introduce this type of organic compound that acts as the antenna, you are able to shift the excitation source for more to the visible. There is a redshift, and in that way get the luminescence. So you can do it using other type of materials, and we are exploring this type of chemistry. I've shown you an example on how we can use silica shells. They are very robust in organic codes, so they are very useful. But in some situations, you might be interested in using, for example, carrageenan, polysaccharides, other type of biopolymers that are biocompatible. So we have been doing that type of research, and the cartoon that I'm showing here is precisely the formation of those type of bionanocomposites, again with the europium and the terbium polyoxometallate that provides the photoluminescent behavior to the final material, to the final composite, and then the polymeric matrix that in this case is a biopolymer extracted from a renewable source. In this case, the carrageenans are extracted from red algae and seaweeds that are abundant, and we can use them, we can extract them, and of course, in this way, we are guaranteeing some sustainability to the process. So this slide allows me to bridge to the next part of my talk. So far, we have been using nanoscience to produce new materials. And if we take a look on this slide, we know, as I said, the matrix comes from a renewable source. It's a polysaccharide. Okay? We can extract it from natural materials. But what about lanthanide? Well, we have already heard a lot about the scarcity of certain elements and how the technological demand for those elements are posing in risk the use of those elements. So, more recently, we start also to address this point. Besides the preparation of materials, in particular nanomaterials, can we use them also to reuse other type of materials that contain critical elements? So this is another way to put as a central idea some of the concepts already addressed by the speakers before. So if you take, for example, the market supply risk and also the use of clean energy by conventional means for the mining and production of materials and the products that use lanthanides, you'll see that on the top of pyramid appear lanthanide elements: dysprosium, neodymium, samarium, europium, and here yttrium, which is a rare element and not. So the concern here is, are we guarantee the sustainability to use these elements in key technologies such as communications, mobile phones, monitors, and so on, even cars, mobility? Well, of course not. There are some limits to the production of this type of products that are based on lanthanide technology. But on the other hand, the increase of electronic waste has increased dramatically in the last years. For example, this plot here shows in the last years the amount of the worldwide production of electronic waste. A lot of them contain this type of elements. So we have here, in principle, we have here an alternative source for this type of elements. The paradigm has to change, not only to produce materials, but also to design materials that will be able to reuse them. So this introduces the second part of my talk, and for that I'll give you an idea of the type of materials that we are developing for the moment, precisely to make the recovery of lanthanides. And again, from old to new, but now with a new perspective, which is the use of old materials, such as magnetite, this material, mineral, the natural occurrence, already known by our ancestors. The old China have invented the compass that is based on magnetite. And gold nanoparticles, which have been used as pigments, at least from the Roman area. The glass that you are observing here is a glass made of silica, normal silica, but it has been stained with the gold nanoparticle. And this pink color, red color that you observe arises because there is a focus of white light inside, and the effect that comes and reach our eyes is precisely this red color due to plasmonic behavior of gold nanoparticles. So this functionality, the ferromagnetism or ferrimagnetism of magnetite and plasmonic behavior of gold nanoparticles that are old materials can be used still in nanotechnology of today. And the type of nanosorbents that we have been using is precisely to merge these properties, the magnetic properties of magnetite, the plasmonic behavior of gold nanoparticles, and then make these hybrid nanostructures, place these hybrid nanostructures, for example, in contaminated water, then allows that the pollutant, molecular compounds such as vestigial pharmaceuticals, organic dyes used in textile industry, whatever, absorb in the material, capture using the magnetic field, the external magnetic field that is applied to the system, and then optically detect the contaminant in order to monitor the process by using, for example, Raman spectroscopy, using the SIRS effect, but can be other type of approach. So this is images, transmission electron microscopy images of this type of sorbents. What you are observing here are cubic type, spinel type, magnetite particles, okay? These particles have been decorated with gold nanoparticles, which in this case are spheres, so are these small spots here, okay? And you can play and you can make this type of gold nanoparticles in a distinct morphology in order to optimize the optical signal, for example, by producing nanostars on the top of the magnetite particles. So the idea is to use these type of hybrid structures as a new sorbents. And it was this concept that we have recently applied to recover lanthanides. So we have used another type of substrate. In this case, we have used graphite nanoplatelets. This is a transmission electron microscopy image of those graphite nanoplatelets, so this type of sheets that spread on the grid. These are the ferromagnetic magnetite nanospheres. They were attached electrostatically using a layer-by-layer deposition process on the graphite nanoplatelets. And again, we use this as new sorbents for aqueous solutions containing the species that we want to remove, which in this case are lanthanide ions. So again, the concept here, we have our sorbents, the magnetic nanoplatelets containing the graphite, okay? So these lanthanides that in aqueous solution are mainly in the trivalent states, although coordinated by different oxo species, but they are cationic species that can be attached to the sorbent, can be collected magnetically, and now an important aspect that has been disconsidered in the literature is the possibility to desorb the lanthanide from the sorbent and reuse the sorbent and take the lanthanide out from the solution. We have made our first experiments, have used systems containing, ternary system containing lanthanum, europium, and terbium dissolved in water. At least after 4 cycles of sorption, the sorbents did not show any loss of uptake efficiency, but of course we have to introduce other type of variables here in these studies. But this, as I said before, this was published just last week, and we are continuing this work. So I'll finish with this central idea, which is in fact to have in mind that in material science, especially from a chemical point of view, when we go to the lab to design new type of materials for useful purposes, of course, we have also to think on the availability of those elements and how can we collect and reuse those elements, particularly when we are dealing with elements that are critical for certain key technologies of today that, as everybody knows, most of the lanthanides are part, although in very small amounts, but they are part of most of technologies that we use today. So the paradigm is not only exploring mining, because as it was said before, in some conditions, they are awful conditions of exploration of those products. So we have to think in other way in reusing, of course, reducing also the consumption, but also to reusing and developing technologies that in the first stage could be less efficient, could be a little bit more expensive, but in the long term will have a positive impact in the next generations. So just let me thank my research group. They have performed all the work, and let me thank you all for your kind attention.
Thank you, Tito, for your excellent talk. I would like to thank all the speakers of this session, all of you to stay until this time, this part of the day. We are a little bit tired, so we kept almost the time, not on, but well, 10 minutes later. So I think that in name of Mr. Minister Manuel Leitor, I declare close this first day session.